One other thing that I forgot to tell you all, I think I emailed it to like one person. That is, there's this huge review section that is super useful beyond the sample midterm or the sample final. So there was this Appendix D midterm exam review. What makes this one nice is it's a bunch of similar questions, and then there's an answer key at the end of this.
Ooh.
And while it's too late to use this now to review for the midterm, you can use that for the final, and there's a big monster final exam review. What I told the morning people that I was a little worried about is that there may be some people that were waiting for Cindy and I to give answers to the midterm so that they could write them down, as opposed to struggling through it and trying to get the answer and not write it down, and then check their answer. And so I floated the idea that we could have a hard deadline for this, like before we go over the answers, and then a soft deadline after we go over the answers. But if we end up with really good grades on the midterm across the board, I don't need to change anything because whatever we're doing is working. So it's just me like being nervous. I don't know that any of you here tonight have any of that issues, and maybe no one has it, and I don't have to worry about it at all. Any thoughts, anything you all feel like you need to say about the midterm, questions, concerns, whatever, or is it just like hurry up and grade it, please?
Hurry up and grade it, please.
Yeah.
I could just hold up the answer key I wrote, and we could just see, here's all the answers. Okay, now you know it.
Yeah.
And hurry up and grade all of our other assignments, please.
Yeah.
What? I didn't grade them all? Yes. Yep.
That's yes, you're going to do it, or yes.
Let me just do something real fast. Fingers crossed. There we go.
This meeting is
So
being recorded.
I'm gonna get this midterm graded tonight. Hopefully everyone's alive upstairs. And we are going to do 7-1. Tonight is going to be really short. In the morning class, we finished everything within an hour. And then we did my stat lab. Cindy, I don't know. I suspect this group has all their my stat lab done.
Mine's done. I don't
Mine
know.
Maybe
is.
I'm wrong.
I have a couple I forgot about. I
So-
was like, hey, I'm on top of everything, got everything done. And then I was like, oh, whoops.
Surprise for 6 more. Yay. So we'll spend this first hour doing this because it is pretty short in terms of the 3 worksheets. And I think you already got one of them done. And then the last hour, I'll just sit here, and if you want to work on it, I mean, you don't have to, but I'll sit here, and if you want to work on it together, we can. I did that this morning with a couple of the 5-3 questions, which were rough. They were quite challenging. So I'm happy. Well, that's what we'll do, if that's okay with you all. So this is the worksheet number 2 for 7-1. And this might even go faster with you all. This is the 133 one for me. And from what I understand, you got the other one done last night, this one. And so does anyone have any questions on this one?
I do have one question.
Yeah.
So I was looking at this last night, and I was just curious. Let me just turn to it. So like on question B, so it will be on the next page.
Oh.
Sorry.
This one,
Yeah.
question 2B?
Yep. So if I wrote this down right, it's 0.5 minus 0.067 equals 0.433.
That's
Good.
what I got.
Okay. So would we not use the 0.067 first because of the 15 being first in the parentheses?
What do you mean by use it first?
Well, like, so gosh, would you get the same answer or do you get a different answer? Like in my mind, I was like, isn't it 0.067 minus 0.5?
You'd get a
No,
negative
'cause that
number,
would be a different answer. Yeah, because then it would be a negative.
and you can't have a negative probability.
Ah, okay.
Here's what's happening. Half of the area is below the mean. Likewise, half is above. So we're taking that total area, and what we're wanting is this area here. So if the whole thing is 0.5 and we're just going to chop off this piece, we're like, take this away. When you take that away from 0.5, you're left with that area. So 0.067 was this little slice at the end. 0.433 is the slice between these two. Those two add together to equal that half.
Okay.
Because it's symmetric, we know that the distance between these two, what is that, 9? If I go 9 units above, what was that, 33? I know that this area here is also 0.067, and that the area between 24 and 33 is also 0.433.
Okay. I just, after I looked at it, I just wanted to make sure I wrote it down, that I was doing it correctly. So,
What you really don't necessarily worry about the order of these. This is always going to be the smallest number first, the largest number second. That's just the convention we use. What you're really focusing on is that this area under the curve is the probability.
okay.
And then you're just determining, well, where is this area? You did this problem already. Back in unit 3, you did it here. It's just when we talked about percentages, we didn't say these percents are areas. We said, oh, this percent of the data is between 1 standard deviation above the mean. That's 34%. As area, that really is just 3.4. But it's also a probability. It's all the same thing. What's happening now is we're saying, well, you're going to learn tomorrow night. You can use a calculator in StatCrunch to say, calculate the area between the mean and say some not standard deviation value, some partial value. Whereas before we had these special memorized ones and we had to ask you about 1, 2, or 3 standard deviations away.
Okay.
So now we're going to be able to calculate any area we want. Here's the other thing. We're going to like spend all of chapter 7 learning about this area and probability, and then it becomes this really tiny little piece of a big puzzle. And it's going to feel like, oh, this is super complicated and whatever. And actually all we need is this. And we just use that in one gigantic formula to do one little calculation that then helps us infer something from a sample to a population. So this is really tiny minor theory that's important to know, but it's like plucking a piece of grain out of a sack of grain. And we're going to dump the whole bag into the blender and create flour and make a beautiful cake. It's going to be so tasty. Okay, so try this one. I don't know that you're going to need 5 minutes on this. It's a chocolate cake. We'll do 5 minutes. I don't want to rush you. See if you can't figure out the connection between a graph and the mean. Notice these words, smallest and largest. And we're really just asking you to make the connection between what does the graph look like with respect to a mean, or how does the mean show up on the graph, and how does the standard deviation show up on the graph? Set a timer for 5 minutes. All right, y'all. That was 3 minutes. Do you feel like you're ready? Or do you need more time?
Question B, I didn't have a problem with, but I don't remember talking about like the smallest mean.
So Eric, when we did them last night, the means were always, I guess they were never like this. So the means were always like the same, I guess. So we didn't talk about them as being like closest to 0 and stuff. So I get why they're confused.
Nice.
Yeah.
Well, good. Let's clear it up. I think the first problem is it's a bad graph, right? There should be a y-axis somewhere
Mhm.
to give you a sense of like this is a start from negative infinity over here, end up at positive infinity over here, and there's a 0 somewhere. We don't quite know where it is. Like 0 could, like the mean of A. Well, first, do y'all get that the mean is the center?
Yes.
So that's the mean of A. Here's the mean of B. Here's the mean of C. Okay, so we know where they are on the x-axis. What we don't know is what their numbers are. It doesn't particularly matter because they're in order. The way we organize the x-axis is smallest numbers on the left, largest numbers on the right. So which mean is the largest?
Okay, so it would be C.
Because it's
Because
furthest
further
to
down
the
the
left.
X. Okay.
Like I could put in a
Alright.
scale here and I could let's
Alright.
just call it 1, 2, 3, 4, 5, 6, right? So C
Okay.
is gonna be the largest number, whether we know what it is or not. So then what's the smallest mean?
That
Oh,
would be A,
a
right?
small A, because it's
A,
close
because
to
it's
X, okay.
furthest to the left. So that's
Yes.
what I'd say. It's farthest left, furthest, what's the difference?
Wouldn't it be closest to the,
We'll say closer to the Y. Well, we don't know. The Y-axis could actually be way over here.
okay.
We don't
so
know.
then- Yeah.
So maybe furthest left is the best general answer for Y.
Okay.
Good, Hope and Chloe, yeah. And then, so you all said that, wait, you said C was the right answer because it's for B?
I got
I'm messing.
I got it flip-flopped. I thought it was asking largest, which would have been the C, but it's asking small, which is A.
For B or
question
for A? Oh,
Question
no,
A.
no, you were right. I asked you what's the largest. You said it correctly. C is
Okay.
the largest.
Oh,
mean.
okay. All right.
But for part B, which one has the largest standard deviation?
B,
B.
B.
What descriptions did you all use?
Short,
because it's short
wide,
and wide.
and
Short
largest
and wide.
spread. That describes my ex-husband.
Oh, okay. I mean, okay.
He has the most spread, Becky.
He does, literally. God. God.
These are posted publicly, so like if someone were to find,
Oh, he'll know. It's nothing I haven't told him already, so.
I thought I had them on. I was gonna do unlisted. Right, most spread is what
Yeah.
we have. Okay, okay. All right, so now we get to practice the same thing that we started with, what you were asking, Nicole. Note, we don't know the standard deviation. If we did, we could do all of this with a calculator. So maybe should I just let you loose, or do we did the thing, right? We know that area is the same thing as probability.
Mhm.
Okay. Let's do the one thing that often gets students. How far apart is 80 and 91?
11.
11.
Just so it's clear for everyone, you did 91 minus 80, right? Got your 11. So if I went 11 below the mean, what number would I find? 69, good. That's 80 minus 11 is equal to 69. So what's going to be the area below 69? This shaded part, what would this be? And why?
0.06407.
Excellent. Why is it that?
Because of symmetry.
Nailed it. That's exactly right. Yes, it's symmetric. So we fold that thing across, we have the exact same area.
Becky,
So-
their answer this morning was because Cindy said so.
I was so
Right.
bummed there was no spot for me to put that on the midterm. 'Cause I was still gonna say
You were
because
supposed to do that.
page 107 said so. That was gonna be one of my answers.
Eric said though, you guys, if you put that on the final exam, he will say -1. So don't say because Cindy said so. You have to
If you
say
said-
because of
107
symmetry.
said so, and then put the real answer too.
Right.
I mean, you could say because Cindy said it's symmetric. I'll accept that. And then, okay, so then this is 0.5. Okay, so I'll just let you all do it.
Okay.
6 little questions, see if you can find them out. Some of them you just have to write the answer that's there. Some of them you're gonna have to do some thingies. Set a timer for 5 minutes. So that was 5 minutes. Y'all want more time? Are you good? All right.
I'm good.
What'd y'all say for 91?
For, 0.06407.
Y'all see that? This is this stuff. It's the part that was actually shaded. So again, there's two goals of this problem: that you connect probability with area, and that you understand the symmetry of the normal curve. Less than 80, everyone said 0.5.
Yes.
Good. Less than 91.
0.93593, and I only gave that many because that's what the decimal.
How'd you get that?
I took 1, subtract 0.06407.
Love it. So we're looking at, here, let me use the highlighter. We're looking at pink, all of this area. And so since the whole thing is 1, if we subtract this amount of area from the whole thing, we're left with all this. Nice. Anyone do it differently? Another way is, we know this is half, and then we would just have to figure out this little piece right here, which happens to be 0.43593, and add a half to that. I'm forgetting the third way.
It is.
You could just add the 0.43593.
Oh, all three, yeah, numbers.
Yeah, all
Yep,
three
that's
added
fine.
together.
We know that this is 0.43593. This is 0.43593. That's right. And then the point, yes, add the 3. Good. How about less than 69? Oh, we already said that, didn't we?
0.06407.
Excellent. Same as the above 91 because of the 11 part. Between 69 and 91.
0.87186.
Yeah, that one. And so hopefully what you're all seeing is that it was this stuff in between here. So what I did to get it is I subtracted the 0.6407 from 5 to get one of them. Then I knew the other one, and then you add them together or multiply them by 2. There's other ways you could get it. Let me make sure I write it down. And then let's see, between 69 and 80.
It's 0.43593.
Nailed it. So that's this piece right here. Okay. Anyone have any questions? Is it so? In my opinion, this stuff is crazy hard for the first time you see it, because it's so strange and things that maybe we're not typically doing. But then once you've seen it, you can't unsee it. And it's going to get it even simpler because we're just going to smash it into a calculator, provided we know the mean and the standard deviation. It's the same thing as the chapter 6 binomial calculations. We just use a different calculator. All right, last thing. So here we are, this large business company, they're looking at travel times to work in the morning. And so we're defining this random variable as the morning commute time. Do you agree that that's a continuous variable? Let me not make that a yes or no question. Why is that a continuous variable?
Because it's something you have to measure. We have to compute. We have to add.
Love it. It's a measurement. I said something this morning about bosses. There's one of the, I forget what he is he business or computer science guys talked about, he was always 5 minutes late to work at one of his jobs, and the boss would start like busting him on it. And he's an awesome guy. He'd be like, I don't care, I'm 5 minutes late, why do you care? I stay I stay an hour late. I could stop staying late and come in on time or whatever. And the boss really wanted them there on time. I don't think it ever happened, which is a cool story. So what we define as on time and late can be down to the millisecond. Okay, so you're going to draw a normal curve with the parameters labeled. This is old school. This is page 263. You're doing this because we handed you the mean and the standard deviation. So draw that with its things. It's good practice. I forgot to put one of those on the midterm. Sorry. I know you were disappointed. And then you're going to draw B. I'm going to write B in symbolic notation. B is written as, let's see, the company is interested in the group of employees that take 45 minutes or more. X is greater than or equal to 45 minutes. I forgot to ask my trick question before. What's the probability that an employee takes exactly 45 minutes?
0.
Oh,
Mm-hmm.
how did you answer so fast?
Because it's impossible.
Why is it impossible?
Because Cindy said so.
Good.
Okay. Because it can have, it says exactly is or
A single line would have no area.
Okay, love it.
There
I
you
just
go.
read that on my notes.
There you
Nice.
go.
Nice. There's
Yeah.
another explanation that might make sense too. How many possible times are there that you could be late? Like how many types of minutes could you be late to work?
How many types of minutes?
Yeah, let's try that a different way.
Like, is there more than one type of?
Well, like I'm saying, like how many minutes late could you be to work? What are all the possible amounts of minutes you could be late? There we go. That's a better way.
Like 1 to 60.
So you could be
Or
1 minute,
more.
2 seconds, 1 minute, 3 seconds, 1 minute, 3 seconds, 1/100th of a second. There's an infinite amount of options of you being late.
And it depends on who you're asking.
Yes. Are they a stickler? Like, I got my stopwatch, here you are. Right, so that's the point of continuous and why the line in exactly equal to, I got this all wrong up here, why it's always 0 is that you're picking one specific time, one option out of an infinite amount of options. And when you divide any number by infinity, it's 0. That's the special thing about continuous distributions. So you're going to see in StatCrunch, the only options are greater than or equal to or less than or equal to when we do calculations. If you recall, with the discrete stuff, you could have an equal to, you could have a less than, a greater than, a less than or equal to, a greater than or equal to. And that's because in a discrete distribution, each number is a specific outcome. In a continuous distribution, it's always a range of numbers that we're talking about because there's just so many of them. So don't be alarmed by that. If you, in terms of this class, if you're working with less than or equal to, they mean the same thing. There's no difference between them because the equal to doesn't really add any area. So with that said, are you all set to do this? Oh, I forgot to add the one thing.
So Eric, when they draw this, make sure we say that they don't have to put in the percentages. It like the empirical rule.
Yeah, this just says
It doesn't say that too.
Yeah.
But you guys remember last night, we didn't put in the 34 because it really, we're doing different percentages. We're doing the area and they're special ones. They're not right at the standard deviations. So we don't really need the 34,
Right.
whatever.
13.5, whatever. Yeah.
Yeah.
Also, you're gonna do lots of drawings later, and StatCrunch gives you the graph.
I know, I love it.
So I'll show you how to just be really
Lazy.
efficient.
No, not lazy. It's being, use your resources.
Yes. You just gotta draw one little thing. So fill this in using these parameters. And then write your two things. If you want a reminder of where the strips are, it's page 179. We'll do 5 minutes, but I'll check in between. Set a timer for 5 minutes. That was 5 minutes. Do you like, does anyone know how I not know, or can someone tell us how I wrote these in? Oh, this is violet. Who knew? Why is the 32 in the middle?
Because it's the
I mean-
mean.
Excellent. Why is 41 this one?
Because the standard deviation is 9, so you add 9 to 32.
Good. I just want to
and
make sure that's everyone's remembering that. I know it's old news stuff. Good, good. So add 9 going up, subtract 9 going down. Excellent. So
What
your
is
job,
It goes, when you're going down 23, 24, 15.
That's
what? Who did that? Let's see. 23 minus 9 is 14. Right? Yeah. And 14 minus 9 is 5.
All right, I
Ouch.
just wanted to make sure.
You put way too much trust in me that I can add. Okay, good catch. I did that on purpose to see if you all were awake.
Eric, I did the same last night to make sure they were awake.
Good.
Not really, but
Yeah. Ouch.
they were awake.
Yeah, that is it. I mean, like you just tell Siri to do it, right? Like, okay. So here's the thing: when you draw this piece, this statement, all we really need is where the 45 is relative to the +1 and +2 standard deviations, which happens to be roughly right here. And then we know that we draw this line above, and then we need to know, well, which way is the sign? It said or more. So because that's a greater than, the area we're interested in is what we call to the right, or above the curve, above the line, as opposed to below. And then we're told what that area is, 0.743. So when you're drawing stuff for me, like, really, yeah, we don't need any of this. We don't even need this. We really just need those 3. Like, that's good enough. The mean, we need to know where that is. And then wherever the particular value that is our borderline between what's above and below. Okay. How'd you all do with the interpretation?
7.43% of all employees take 45 minutes or more to drive to work. That's
Love it.
That's what I have.
Portion.
That's the proportion one. Key word here is of all
Mhm.
employees. What I said this morning was, this is looking at the forest and admiring all the trees and seeing what percentage of them are green versus orange. So 7.3% of all employees take more than 45 minutes to get to work. Awesome. What's the other one?
The probability that a randomly selected employee takes longer than 45 minutes to drive to work.
Is 0.0743. Nailed it. Yes. So note, in that case, we're selecting just once. We're plucking out a tree and saying, what's the chance that this tree is green compared to all the other trees? You can write any one of these as a decimal, a percent, or a fraction if you want, because it's all the same thing. I think when we talk about proportions, we often think of it more as a percentage. But yeah, okay, so the probability of randomly selecting an employee that takes more than 45 minutes is 0.0743. You could also say there's a 7.43% chance of randomly selecting an employee that takes more than 45 minutes. there's a little leeway in how you say those, but yeah, those are the two interpretations.
Oh, okay, so for the probability, I put, instead of the 0.0743, I put 7.43%.
Totally fine.
Okay,
That's it, same thing.
yeah, I just want to make sure that, okay.
Here, you want me to really blow your minds? You could do 743 divided by 10,000.
No, it's okay, you don't have to do that.
No one wants to do that one, right? But that's just turning this decimal into a fraction. That's all that is. What is it? Tenths, hundreds, thousandths, 10,000ths place. So 743 over 10,000. But
No.
Yeah.
Excuse me.
Okay. So tomorrow you're going to learn how to do these calculations. You're going to learn this Z, and this is the one that matters the most. It's the standard normal curve and the Z critical values. This might look all kinds of challenging. It's just, can you type it into StatCrunch and spit it out? This is the most important thing that you will learn tomorrow. It's really the only thing you use in chapters 9, 10, and 11. It's called the critical Z value. Sounds all kinds of crazy. It's not. You did do 7.3. And 7.3 is a very basic section that is really important, and it also is not a big deal. So if you remember section 1.1, we talked about the process of statistics, how we come up with a question. From that question, we define the population that the question is like based off of. From that population, we randomly select a sample. From that sample, we generate a set of descriptive statistics. Sounds like midterm, right? From those sample statistics, what we're about to learn how to do is make an inference about the population. So we do some analysis about those descriptive statistics and use them to describe the population. Well, one of the conditions to do that is that when we draw the sample from the population itself needs to be approximately normal. What we mean by that is if we were to graph all of the data values from the population, we'd want a graph to roughly look like this, where the center was the mean. And then there's the standard deviation that spread it out, and it was approximately half was above the mean and half was below and all that. It's part of the reason why the data set has to be normal for that mean and standard deviation interpretation sentence to make any sense. Because if it's not normal, it isn't on average that a particular thing is the mean, give or take the standard deviation. Like, that's not true. So we come up with a measurement of how to determine if the population is normal. Remember, you don't know what the population is. Like, you don't know that data value or that data set because it's probably too expensive to collect it. Too many things in it. So what we do is called a normal probability plot. And that's what you're seeing here. Normal probability plots have a y-axis that's a normal quartile and an x-axis that's the data values. So you have to be careful because we have two other graphs we know about. One of them is the scatter plot from chapter 4. And that's where we mashed two variables together. We made one the explanatory and one the response variable. And we looked at the two variables graphed. And we thought, oh, does this look linear or not? We then had a residual plot. Like, after we got that line, we calculated the distance between each data value in that line and graphed the residual plot. And remember, the residual plot, we said, hey, is that graph randomly dispersed? If it is, then a linear equation is an appropriate model. If it's not, then it's not appropriate. Throw everything away. Well, this is a normal probability plot, and all it tells us is if the population that we collected the sample from is normal. And the way to look for it is the same as the scatter plot. Does it look approximately linear? If it does, then the population is normal. If it doesn't, then the population is not normal. And if you're interested in grad school or an undergraduate degree in statistics, which I feel like we all are because we're just loving this course so much, you'd learn more tools to mess with that. So for now, what I'm interested in is that you can name the graph you're seeing, and that you can state either it's approximate linear or it's not. Even if you're wrong about that, I don't care as much. Like when I see this, my mind goes to that shape. That doesn't look linear to me. That looks logarithmic. And you may not even know what that is, and I wouldn't expect you to. So my answer to, is it reasonable to assume the sample is coming from an approximately normal population, is no, because the normal probability plot is not approximately linear. And if you had said yes, the normal probability plot is approximately linear, I would have been mostly happy because I knew you knew what you were looking at and you knew the criteria. Maybe you're not as good at seeing the basic shape, but that's, you know, that takes experience, and also like there's other more powerful tools. So as long as you know what you're looking at and how to evaluate it, I'm happy. What's your answer to 2?
Yes.
Yeah, that looks approximately linear. That R value is going to be pretty close to 1 if we were to do that. So here we take the same script. Yes, the normal probability plot. The reason I say this, I'm like spending so much time on this, is often on final exams, people get this problem wrong because they say, yes, the data looks linear. No, they say something, they say something that makes it very clear they don't know what graph they're looking at. Like, yes, the values are increasing. Well, okay. Anyways, so the normal probability plot is approximately linear. Yay, we did that one. Try Cindy's. I'll give you 2 minutes. Put a timer for 2 minutes.
You guys don't have to turn this in for me, but yes, do it.
I usually skip these.
I
too.
saw Becky looking down. I
What
saw
page
you,
is it on? I'm sorry.
Yeah,
I was
what-
looking, I didn't see
I saw ya. I saw ya.
Okay. I was like, wait a minute, that's not on the inside.
Oh, I didn't
Bill-
look at the assignment sheet.
No, do it. Do it. Just let him do it, Eric.
Yeah,
It's
no,
good
that's fine.
practice.
I just didn't know what page it was on. Okay.
Oops.
We got this. I think.
So that was 2 minutes. Enough time? So what's 1?
Yes,
Why?
normal probability plot is approximately linear.
Nailed it. 2,
No,
cause?
normal probability plot is not. Is it approximate or approximately linear? What's,
I think what is linear is a noun, and so approximately is an adjective, and
okay.
approximate is a verb. So you want it approximately? I don't know. Doesn't matter.
Well, I want to
Good
make sure I
question.
get it right. So is it approximate or approximately? Because I thought you wrote down approximate.
I
but-
wrote APPR.
Oh, well, shit, okay.
So I think the correct word is approximately linear, because it's like
Okay.
an adjective of that noun, but
But it's okay to abbreviate, right?
it's, I mean, yes.
All right, I'm gonna do that.
I mean, look at me spelling probability up here. It's prob. Maybe if we get some teenagers saying it, it'll happen. Get it up on TikTok. It'll
Right.
go for an hour or two, maybe. Awesome. That's it. That's all you need to know about the normality. What you're going to discover in chapters 8, which is heavy theory, and then 9 and 10, this is a condition that has to be true in order to do a test. So sometimes we'll just say, hey, assume the population is normal. Other times we'll give you this graph and say, hey, can we do the problem? And your answer will be, no, it's not approximately linear, the normal probability plot, or yes, it is. So that's where this shows up. Okay, that's it.
Good night.
Yeah, if you earned it, like you all did your thing last 2 nights ago, whatever. If you're all caught up, or you're like sick of seeing me or whatever, take off. I will stay here and leave this on until there's no one else here. Like if you want to share screens and we work on Stat Lab together, that's awesome. If you want to ask me questions about anything, that's great. Otherwise, this is all we need to cover for tonight, and we're right on track to finish by the end of the semester.
So you get a whole extra hour to start grading exams.
Yes. If I can get the girls to bed,
Right,
which
Jessica.
is easier if I'm there. I will
Too
grade. They
funny.
will be done tonight. That I will.
I'm just giving you a hard time. I'm just.
You know, you should. It's motivation. Yes, I'm going to get them graded tonight.
Not-
Do we get to hold you to that?
Right.
Yes, you can.
Right, Alexa.
Like, what happens if I don't? Like, what's the punishment?
You're gonna have to buy a round of beers.
Right.
Okay, I'm probably gonna have to do that anyways. But okay.
Oh,
that's
Eric,
fair.
I heard that Laura emailed you and is holding, yeah.
Laura was like, I am checking every day. Grade it, and guess who got theirs graded this morning?
All right, we're good. Well, I need to hound you.
Is that all we have
Well,
to do?
That's all you have to do is hound me.
Hey,
Yes.
Eric, I need my stuff graded, man.
Okay.
Oh, that's funny.
Oh, I know it's bad. Talk to me.
So, no, well, well, Cindy, what are we doing tomorrow then? Did we've covered all of 7? What are we doing tomorrow?
No, we haven't done 7-2.
Oh, okay. We just don't have anything due for it this week. Is it next week that we have stuff due for it? Or we just,
Night. Thanks, Will.
Yeah, for 7-2,
Hey,
yeah.
Will.
Yes.
all right.
Just kidding.
Okay. Well, I'm
Awesome.
good. I'm gonna go eat dinner and